constant product AMM, x times y equals k. And essentially swapping between x tokens and y tokens is equivalent to moving the state of the pool from one point on the curve to another point. In this particular example, we are swapping 5x tokens in exchange for 10 y tokens, and the execution price is simply dy divided by dx, which is equivalent to the slope of this curve, which is just 2. And if you want to compute the spot price on any particular stage along this bounding curve, what you can do is computing dy and dx, where both dy and dx approaches 0. It will be a reminder of college calculus. That's just a gradient at that particular point along this bounding curve, which is just y divided by x. And there's also this concept of trading slippage, which is the difference between the spot price and the execution price. In this particular example, the spot price is 3 and execution price is 2, so trading slippage is 1. Ideally speaking, when we are talking about improving capital efficiency, what we are talking about is really reducing the trading slippage, assuming we have the same amount of capital available within this group. Also, as you guys probably already know, constant product AMM at this very basic version suffers from low capital efficiency, meaning if we are making a swap, we suffer from high trading slippage. So what exactly is going wrong with this bounding curve? There are two problems. The first one is that for certain token pairs, especially like packed token pairs like USDC against USDT, or maybe SUI against liquid state SUI, this x times y bounding curve is not necessarily the ideal bounding curve. The second problem is that if we look at the price of y denominated by x or vice versa, it actually ranges from 0 to positive infinity, looking at the gradient of this bounding curve, which is the liquidity is actually distributed from across the entire price range from 0 to positive infinity. But most of that price range actually will never be touched upon. So meaning that the liquidity distributed around that price range are not going to be used. Ideally speaking, instead of like distributing your liquidity across the entire price range, you would like the user to select a customized price range to distribute liquidity over. So let's see how we can solve both problems. In terms of the first problem, like designing a better bounding curve for stable like pairs or packed pairs, maybe instead of having a like x times y bounding curve, like the dash purple curve shown here, what we can do is we can have a constant sum bounding curve with the slope set at 1, like the dash red line shown here. So along this bounding curve, regardless of how you move along this bounding curve, the execution price you get is always 1.0 because the slope is 1.0, meaning the trading slippage you get is always 0. But like this bounding curve has a problem because like the token x or y could actually dry up once you reach the boundary points, like when it intersects the x or y axis, which is not ideal. What if we can maybe take a middle ground between the red curve and the purple curve, and we end up with this blue curve? This is the standard stable swap invariant. This curve does not intersect with the x-axis or the y-axis, so it's never going to drain up the x token or y token. And suppose you are moving along this blue bounding curve, like across the range close to the center, essentially the slope you get is always close to 1.0, meaning the slippage is always close to 0. So now we have solved the problem for packed token pairs, but this bounding curve is not really applicable to uncorrelated pairs. For example, SUI against USDT. And the second problem, that liquidity are still distributed across the entire price range. So can we come up with a mechanism to solve both problems? Turns out we can with a concentrated liquidity market maker. Let's see how that works. So suppose we have a regular constant product AMM bounding curve, like we shown on the green curve here. Let's suppose we move this curve closer to the origin, And we cut off the sections that crosses the x-axis and the y-axis. Then we end up with this orange curve here. Note that the orange curve is actually equivalent to the green curve between section A and section B. And like the slope along the green curve between A and B is equivalent to the slope of the curve on the green curve, meaning that the spot price of these two curves are equivalent to each other. Also, specifically, if you are trying to swap tokens on the green curve, like you want to say, starting from this point, swap DX tokens in exchange for DY tokens, like you can always find a corresponding curve, corresponding point on the orange curve, where you swap DX tokens, you always get back a DY amount of Y tokens. Essentially, what this implies is that you are constructing the same amount of equivalent liquidity using this orange curve as if you had the green curve, but with much less capital because a point on the orange curve always has lower x and y values than corresponding point on the green curve, as long as the price does not cross the boundary points A and B. So this is essentially how concentrated liquidity AMM works. By selecting a customized price range, you can achieve the same, you can achieve the equivalent liquidity as the regular constant product AMM with much less capital. Actually, it depends on how closer you move the green curve to the origin. In other words, depending on how you select the price range, you can even achieve like 100 times or even 1,000 times better capital efficiency. And you can also get improved LP rewards. So that's good for the theories. Let's look into how you actually provide liquidity on a concentrated liquidity market maker in practice. So these two screenshots are taken from the MoveEx, the app running on the Sui.net. On the left-hand side, you can simply select a customized price range by setting the min and max price and uniformly distribute your liquidity across that price range. You can also see these gray area here representing the liquidity distribution across the entire price range. On the right-hand side, you can also provide single-sided liquidity with one tokens, as long as both the min price and max price stays on the same side of the spot price, which is represented as the pink line here. Okay, so now we have concentrated liquidity. You might be wondering, is there anything we can do on top of concentrated liquidity market maker to improve the capital efficiency even further? Turns out we can. Let's see how. Remember, in the previous graph, we have a single LP positions on the concentrated liquidity market maker, which is equivalent to uniformly distributed liquidity between two price ranges. So now instead of having one LP positions, you can actually come up with multiple LP positions to form a liquidity distribution around the spot price. And you can concentrate more liquidity around the center of the spot price and have slightly less liquidity at prices further away. In this way, you can improve the capital efficiency even further compared to a single LP position. Also note that liquidity is most efficient when they are concentrated right around the spot price, which means if the spot price changes, you probably should move your liquidity distribution to maintain your capital efficiency. Say if the spot price increases, you should probably move the liquidity distribution rightward a little bit. If the price decreases, you should move it leftward a little bit. This gives rise to actively manage LP positions from passive LPs. Actually, essentially, concentrated liquidity market maker opens up a wide spectrum of quantitative strategies to actively and dynamically manage and improve LPs. So that's good enough for the theories. Let's look into how different mechanisms work in practice. We have selected the top axis on the theory, Uniswap V2 representing for constant product AMM, curve representing for stable swap, Uniswap V3 representing concentrated liquidity market maker. You can see that the daily trading volume denominated in million US dollars for stable swap and concentrated liquidity market maker is actually higher than constant product AMM because like they incurs much less trading slippage and is favored by the users. Specifically with the concentrated liquidity market maker, we can actually achieve like 10 times the trading volume and close to 3 times the PDL, despite the fact that like the Uniswap V2 has a first runner advantage. So that's good enough for the AMM. Let's touch upon a little bit on central limit order book, or also known as the clock. I guess like many of you probably have interacted with a central limit order book before. Like central limit order book is the default market making mechanism on centralized exchanges like Binance, like Coinbase, etc. This is a very standard like central limit order book UI UX. You probably are already familiar with this. Like on the left-hand side, you can interact with the cloud by say submitting a limit order where you have to set a limit price and the amount of quantities to trade the tokens, or you can submit a market price where you only need to fill in the total amount of quantities. On the right-hand side, you can see the market depth, and like you can see that the entire price range is divided into small price levels, like with like increment of maybe 0.1 or 0.2. There will be some open, unfilled limit orders on each price level, and the total amount of quantity on each price level is simply the sum of the quantity of all the open orders, all the open limit orders. So in terms of interacting with the clock, you either use limit orders